Okay, problem 26. A parallel plate vacuum capacitor has 8.38 joules of energy stored in it. The separation between the plates is 2.3 millimeters. If the separation is decreased to 1.15 millimeters, what is the energy stored? A, if the capacitor is disconnected from the potential source so the charge on the plates remains constant, or B, if the capacitor remains connected to the potential source so the potential difference between the plates remains constant. So A, Q constant. Okay, so from the back of our chapter, we know that the potential energy stored in a capacitor is 1/2 CV squared, which, using our Q equals CV equation, we can also write as 1/2 QV or Q squared over 2C. So the distance changes the capacitance between the dudes. According to capacitance equals E naught A over D. So the first thing we want to do is use our initial energy to find this capacitance, assuming that the charge is constant. So if we plug this in for capacitors, we care about charge and we care about capacitance. So U equals 1/2 Q squared over C, or Q squared over 2 E naught A over D. So if our initial potential energy at a distance of 2.3 millimeters, all of this junk is going to remain constant when we decrease that distance. So we're having our charge remain constant, E naught to constant, and the area of the plates isn't changing. Cool? So I'm just going to say junk. So U equals D times junk. Alright? So the value of junk is equal to U divided by D, which initially U is 8.38 joules and D is 2.3 times 10 to the minus 3 meters. So if I plug that into my handy dandy calculator, 8.38 divided by 2.3 times 10 to the minus 3. That gives me junk equals 3643.5 joules per meter. Alright. So now remember, junk stays the same because the charge is constant, the area of the plates is constant. So my new potential energy, D times junk, D is now 1.15 times 10 to the minus 3 meters times junk, which is 3643.5 joules per meter. Which is 4.19 joules, or half of what we started with. So we're cutting the distance in half. So since our potential energy depends on distance, if we have the distance, we're having the potential energy. Cool. Alright, so now for part B, where we care about the potential being constant. So V constant. So now we want to use our potential energy equation that has capacitance and voltage. So U equals 1/2 CV squared. So like before, we want to plug in for C our values here that depend on the distance. So we have 1/2 E naught A over D times V squared. So now our D is on the bottom for U. So junk. So we can do this mathematically like we did before, or we can look and say, okay, I'm cutting my distance in half again. So D is going to 1/2 D. So D is getting cut in half, but since it's on the bottom, it means it's doubling my potential energy. So if U equals junk over D, and I cut D in half, it's going to multiply it by a factor of 2. So my new potential energy is going to be twice of what I started with. So 8.38 times 2 is 16.76 joules.